Hi everyone. Welcome. If you are here right now, it is probably because you are ready to rest. You are ready to let go of the day, to let your thoughts slow down, and to drift somewhere quiet and peaceful. And that is a very good place to be. Tonight, we are going to take a very long, very calm journey together. We are going to follow water. Just water. One of the most familiar things in all the world, and yet one of the most quietly extraordinary things that exists anywhere in the universe. Water has been on this earth for billions and billions of years. The same water that falls as rain tonight has existed in oceans, in clouds, in rivers, in glaciers, in living creatures in the deep underground. It has traveled farther and been more places than any of us can truly imagine. And we're going to take that journey slowly tonight. There is no rush. There is no destination we need to arrive at. We are simply going to move gently through the story of water, one soft thought at a time. So if you are lying down, feel free to close your eyes. Let your body settle. Let your breath slow. You do not need to hold on to anything I say. You do not need to remember any of it. Just let the words wash over you, slowly, gently, like a very quiet stream. We will begin now. The water on Earth is incredibly, almost unimaginably old. Most of it arrived here billions of years ago, long before any life existed on this planet, carried by icy comets and asteroids drifting through the solar system. These space objects, traveling slowly through the darkness of space, were filled with frozen water. And when they collided with the early Earth over millions and millions of years, they left their water behind. So when you hold a glass of water in your hand, you are holding something that is older than the mountains, older than the oceans, older than almost everything you can see. That same water has been cycling around this planet ever since. And we can take a moment to notice what a quiet, remarkable thing that is. Ancient water, resting in your glass, resting on this earth. Water is made of just two elements, hydrogen and oxygen. Two atoms of hydrogen joined to one atom of oxygen. It is written as H2O, and it is one of the simplest molecules that exists. And yet, hydrogen and oxygen are among the most abundant elements in the entire universe. Hydrogen, in particular, was one of the very first elements to form after the Big Bang billions of years ago. So in a very gentle way, water carries within it a connection to the very beginning of everything. When we breathe near a glass of water, or when rain touches our skin, we are in contact with something made from the oldest stuff in the cosmos. Two simple elements joined quietly together, making something that every living thing on Earth depends on. Slowly, gently, water reminds us how connected everything is. Scientists believe that most of the water currently on Earth arrived here approximately 4 billion years ago. That is 4,000 million years. To try to understand how long that is, consider that the dinosaurs lived about 65 to 200 million years ago, and 4 billion years is more than 60 times longer than that. The water in your body right now has been on this planet since long before the first fish swam in the ocean. Long before the first flower bloomed, long before the first human ever looked up at the stars. It has been here, cycling and moving slowly and endlessly, through the atmosphere, the oceans, the rivers, the ice, and through every living creature that has ever existed on this world. There is no need to rush through that thought. Just let it settle gently. Earth is, as far as we know, the only planet in the solar system where water naturally exists in all three of its states at the same time. Liquid water fills our oceans and rivers. Solid water exists as ice in the polar regions and on mountaintops. And water vapor, the gas form of water, floats invisibly in the air all around us all the time. This is something quite rare in the universe. It requires a planet to sit at just the right distance from its star, with just the right atmosphere, to allow all three states to coexist. Earth sits in what scientists gently call the habitable zone, not too hot, not too cold. And because of that, water can be in all three of its forms simultaneously, moving between them constantly in the great slow cycle that keeps our planet alive. Even in the driest deserts, even in cold winter air, there is water vapor present. You cannot see it, you cannot feel it in the way you feel rain, but it is there floating invisibly as individual molecules drifting through the air. Humidity is simply a measure of how much water vapor is in the air around you. In a tropical rainforest, that number can be very high. In a desert, it is very low, but it is never truly zero. When you exhale right now, wherever you are breathing out water vapor. Your warm breath meets cooler air, and on cold mornings, you can see it, that little soft cloud that forms in front of your face. That is your own water, released gently into the world. And we can take a moment to notice that quiet exchange between you and the air. Gently moving forward, a single molecule of water is so incredibly small that it is almost impossible to picture. If you could line up water molecules side by side, it would take about 10 million of them to stretch across just 1 millimeter. 1 millimeter is roughly the thickness of a credit card. So in that tiny width, you could fit 10 million water molecules in a row. And in a single drop of water, just one small drop, there are approximately 1.5 sextillion water molecules. That number is a 1 followed by 21 zeros. And yet, every single one of those molecules behaves in the same quiet, predictable, beautiful way. Each one made of 2 hydrogen atoms and 1 oxygen atom, arranged at a gentle angle, like a tiny, invisible pair of open arms, ready to bond with its neighbors. Quietly, gently, in numbers beyond imagining. Water is often called the universal solvent. This means it can dissolve more substances than almost any other liquid on Earth. The reason for this comes down to the shape and electrical nature of the water molecule. Because of the way hydrogen and oxygen are arranged, one side of a water molecule has a slight positive charge, and the other side has a slight negative charge. This makes water very effective at pulling apart and surrounding other molecules, dissolving them. Salt, sugar, minerals, gases, many organic compounds. Water can dissolve all of them to some degree. This is one of the reasons water is so essential to life. Inside your body, water carries dissolved nutrients, dissolved oxygen, dissolved waste products, all moving gently through your blood and cells. The universal solvent quietly doing its work slowly, endlessly. If you have ever seen a small insect walking on the surface of a pond, you have seen surface tension at work. Water molecules are strongly attracted to each other, and at the surface of the water, where there are no water molecules above them, the molecules pull inward and sideways, creating a kind of soft, invisible film. This film is strong enough to support small insects like water striders, which can walk across the surface of still water without breaking through. Surface tension is also why water forms round droplets. A sphere is the shape that holds the most volume with the least surface area, and surface tension pulls water into that natural, peaceful roundness. Watch a raindrop on a window sometime. It sits there, quietly round, quietly whole, pulled into itself by those tiny molecular attractions. Most substances are denser in their solid form than in their liquid form. But water is different. Ice is actually less dense than liquid water, which is why it floats. This happens because when water freezes, its molecules arrange themselves into a hexagonal crystal structure, a very regular open lattice, which takes up slightly more space than the looser arrangement of liquid water molecules. And this is something extraordinarily important for life on Earth. When lakes and ponds freeze in winter, the ice floats on top. It forms an insulating layer that keeps the water below it from freezing solid. The fish, the plants, the microscopic creatures, they survive the winter in the liquid water beneath the ice. If ice sank, as most solid substances do, lakes would freeze from the bottom up, and most aquatic life would not survive. A quiet, gentle quirk of chemistry that makes life possible. The water cycle, the continuous movement of water around the planet, is one of those processes that has no real starting point and no real ending point. It is a circle, or perhaps more accurately, an endlessly flowing loop. Water evaporates from the ocean's surface, rises into the atmosphere, forms clouds, falls as rain or snow, flows into rivers and groundwater, and eventually makes its way back to the ocean to begin again. But even that description is too simple. Water takes detours, through glaciers that hold it for thousands of years, through underground aquifers that hold it even longer, through the bodies of plants and animals. The cycle is always moving, always flowing, at different speeds in different places. Some water completes a cycle in days. Some takes millions of years. And we can take a quiet moment to think about where the water around us might be in that great, unhurried loop. Now, as we continue, let us move gently toward the ocean. About 71% of the Earth's surface is covered by ocean. That is more than 2/3 of our entire planet covered in water. When you look at a globe, the vast blue expanses seem peaceful, quiet, enormous. And they are. The total volume of all the world's oceans combined is approximately 1.3 billion cubic kilometers of water. That is a number so large that it has very little meaning to our human minds. But perhaps this helps. If you could take all that ocean water and pour it into a cube, that cube would be about 10,000 kilometers on each side, roughly the distance from one side of the Earth to the other. All that water, quietly surrounding the continents, slowly moving, breathing with the tides, giving and receiving life. While the ocean covers most of our planet, it is also remarkably deep in places. The average depth of the world's oceans is approximately 3,700 meters. That is about 3.7 kilometers, or more than 2 miles straight down. And in the deepest places, like the Mariana Trench in the Pacific Ocean, the water descends to nearly 11 kilometers below the surface. That is deeper than Mount Everest is tall. Down in those great depths, the pressure is immense, the temperature is just above freezing, and it is completely, perfectly dark. No sunlight reaches those places, and yet life exists there. Strange, slow, quiet creatures that have adapted to the crushing pressure and the cold and the dark. Life, finding a way in the most distant, most silent parts of the ocean. Water has a remarkable ability to absorb and store heat, and the ocean uses this ability on a planetary scale. The ocean absorbs more than 90% of the excess heat that has been added to the Earth's system over recent decades. This heat capacity is one of the reasons that coastal cities tend to have milder climates than inland cities at the same latitude. The ocean moderates temperature, warming the land in winter, cooling it in summer, releasing heat slowly and steadily. When you are near the sea and you feel that soft, gentle breeze coming off the water, you are feeling the ocean sharing its stored warmth with the air. Slowly, gently, the ocean breathes its heat into the world, keeping the climate more stable, more even, more livable than it would otherwise be. Ocean water is salty because over billions of years, rain has washed minerals and salts out of rocks and soil on land, carrying them down rivers and into the sea. The ocean has no drain, so these dissolved minerals have accumulated over geological time. The most common dissolved substance is sodium chloride, ordinary table salt. But the ocean also contains magnesium, sulfate, calcium, potassium, and dozens of other dissolved elements. The average salinity of the ocean is about 3.5%, meaning about 35 grams of dissolved salts per liter of water. If you could take all the salt out of all the oceans and spread it evenly over all of Earth's land surface, it would form a layer about 166 meters thick, taller than a 50-story building. All of that dissolved quietly, invisibly, in the soft blue water of the sea. Inside the ocean, water moves in great, slow, organized rivers called ocean currents. Some of these currents flow near the surface, driven by wind. Others flow deep beneath the surface, driven by differences in temperature and salinity. Together, they form a vast global system sometimes called the ocean conveyor belt, or more formally, the thermohaline circulation. Cold, salty water near the poles sinks slowly toward the ocean floor, while warmer water near the equator flows along the surface toward the poles. This great, slow circulation carries heat around the planet, influencing weather patterns and climates across entire continents. The Gulf Stream, for example, carries warm water from the Gulf of Mexico northward along the eastern coast of North America and across to Western Europe, helping to keep places like the British Isles warmer than they would otherwise be. Slowly, gently, the ocean moves heat around the world. Let's take a quiet moment to think about the depth of the sea. We often think of forests when we think about oxygen, but about half of all the oxygen produced on Earth comes from the ocean, generated by tiny photosynthetic organisms called phytoplankton. These microscopic creatures drift near the surface of the ocean, where sunlight reaches, and they use that sunlight to convert carbon dioxide and water into oxygen, just as plants do on land. There are so many of these tiny organisms, trillions upon trillions of them, that together they produce an extraordinary amount of oxygen. Every other breath you take was made possible by creatures too small to see, floating quietly in the sunlit upper layers of the ocean. And we can take a moment to notice that breath, that soft, easy rise of your chest, that quiet exchange of gases, brought to you in part by the sea. Sound is a wave of pressure that moves through a medium, air, water, or solid material. In air, at room temperature, sound travels at about 343 meters per second. But in water, sound travels much faster, about 1,480 meters per second. That is more than 4 times faster. This is because water is much denser and less compressible than air, so pressure waves move through it more quickly. Whales take advantage of this. Blue whales, the largest animals ever known to have lived on Earth, communicate with deep, low sounds that can travel through the ocean for hundreds or even thousands of kilometers. Their slow, long songs move through the water at great speed and great distance, carrying gentle messages across the quiet depths. In the deep ocean, sound is the light, the way creatures find each other across the vast, dark silence. Every day, the ocean rises and falls with the tides. This quiet, rhythmic movement is caused primarily by the gravitational pull of the moon. As the Earth rotates, the side of the planet facing the moon experiences a slight gravitational pull toward it, causing the ocean water to bulge outward slightly in that direction. There is also a corresponding bulge on the opposite side of the Earth, caused by inertia. As the Earth rotates, different coastlines pass through these bulges, experiencing high tide and then low tide roughly twice each day. The sun also has a tidal effect, though smaller than the moon's. When the sun and moon align, their combined pull creates the largest tides, called spring tides. When they are at right angles, the tides are gentler, called neap tides. The tide goes in, the tide goes out, slowly, reliably, for billions of years. Despite the ocean covering most of our planet, we have only explored a small fraction of it. Some estimates suggest that more than 80% of the ocean floor remains unmapped and unvisited. The deep ocean is difficult to explore. The pressure is immense, the darkness is complete, and reaching those depths requires specialized equipment. In some ways, we know more about the surface of the moon than we know about the deepest parts of our own ocean. There are likely thousands of species down there that we have never seen, creatures living in the cold and dark, going about their quiet lives completely undiscovered by human eyes. The deep ocean is one of the last great unexplored frontiers on Earth. A vast, quiet, largely unknown world, resting just beneath the surface of the sea. In certain places and under certain conditions, the ocean glows in the dark. This phenomenon is called bioluminescence, and it is produced by tiny living organisms, certain species of plankton, jellyfish, fish, and other sea creatures, that can generate their own light through chemical reactions in their bodies. When waves disturb the water at night, millions of these light-producing plankton can light up all at once, turning breaking waves into soft, ghostly blue fire. It has been reported by sailors for centuries, a mysterious glowing of the sea in the darkness. Some coastlines around the world are known for this gentle light. Imagine standing on a beach at midnight, watching the waves come in, each one glowing softly blue as it breaks on the shore. The ocean breathing in the dark, quietly illuminated by life too small to see with the naked eye. Gently moving forward toward the clouds. Clouds are not made of steam, and they are not made of gas. They are made of liquid water, tiny, tiny droplets of liquid water suspended in the air. Each droplet is so small, perhaps 1/100th of a millimeter across, that it can float in an air current without falling. Clouds form when warm, moist air rises and cools, and the water vapor in that air condenses around tiny particles of dust, pollen, or sea salt. These particles are called condensation nuclei, and they are everywhere in the atmosphere, too small to see, drifting invisibly, waiting for water to find them. When enough droplets come together in one place, they become visible to us as a cloud. A soft, white, drifting thing made of millions of tiny spheres of water, floating quietly in the sky, catching sunlight, casting gentle shadows. Looking up at a white, fluffy cumulus cloud on a sunny day, it is hard to believe it has any weight at all. It seems so light, so airy, so effortless. But a typical cumulus cloud contains somewhere around 500 million liters of water in the form of tiny droplets. And that water has weight. The average cumulus cloud weighs approximately 500 million kilograms, about the same as 100,000 elephants. Yet it floats. It floats because those water droplets are so incredibly tiny and spread so far apart through such a large volume of air that their weight per unit volume is actually less than the air beneath them. The cloud floats the same way a very light foam might float on water. All that weight, drifting quietly overhead, gently, peacefully, invisible in its heaviness. We almost always picture a raindrop as a classic teardrop shape, round at the bottom, coming to a point at the top. But that is not what a falling raindrop actually looks like. Small raindrops, less than about 2 millimeters across, are nearly perfect spheres, pulled into that round shape by surface tension. Larger raindrops are flattened on the bottom by air resistance as they fall, giving them more of a rounded, slightly flattened shape, almost like a small hamburger bun. Very large raindrops become so flattened that they can split into smaller drops mid-fall. The teardrop shape we imagine comes from water dripping slowly off a surface, where surface tension holds the forming drop into that classic pointed shape before it falls. The actual falling drop in the air is rounder, calmer, more quietly complete. Raindrops, despite falling from high in the atmosphere, do not fall at extreme speeds. Small raindrops fall at roughly 2 meters per second, about the speed of a leisurely walk. Larger raindrops fall faster, at perhaps 9 meters per second. Terminal velocity, the maximum speed a falling object reaches when air resistance balances gravity, keeps raindrops at these gentle paces. If it were not for air resistance, a raindrop falling from a cloud several kilometers high would reach the ground at a dangerous speed. But the air slows them, gently, all the way down. So when rain falls on your face, it arrives with a soft touch, not a harsh one. Each drop having fallen for many minutes through the cool sky, slowed and gentled by the air, arriving quietly, softly, on the earth below. High in the sky, rain begins to fall. But not all of it makes it to the ground. In very dry or hot conditions, raindrops can evaporate while they are still falling, turning back into water vapor before they reach the surface. This phenomenon is called virga, rain that falls from a cloud but disappears in the dry air below. You can sometimes see it from a distance, a cloud with what looks like gray streaks hanging below it, like a curtain that doesn't quite reach the floor. The rain is there, falling, trying to reach the earth, but the warm, dry air below the cloud dissolves it back into vapor. The cloud reaches down toward the land, and the land never feels the touch of rain. It is a gentle, wistful sort of thing, and we can take a quiet moment to imagine it. There is no need to rush. Every snowflake, no matter how complex its design, is built on a hexagonal, six-sided structure. This is because of the way water molecules bond together when they freeze. Water molecules arrange themselves in a hexagonal lattice when they form ice crystals, and this basic six-fold symmetry is preserved and elaborated as the snowflake grows. The temperature and humidity that a snowflake encounters as it falls through the atmosphere determine exactly how its arms grow and branch, which is why no two snowflakes are exactly alike. But they all share that fundamental six-sided geometry. It is a quiet, beautiful example of physics expressing itself in nature. The molecular bond angle of water, reflected perfectly in the delicate, visible shape of each individual snowflake, falling slowly through cold winter air. At any given moment, the Earth's atmosphere contains about 12,900 cubic kilometers of water in the form of vapor. That is enough water to cover the entire surface of the Earth in a layer of water about 2.5 centimeters deep. And this water is constantly in motion, evaporating from the ocean's surface, carried by winds, condensing into clouds, falling as rain or snow, and then evaporating again. The average water molecule spends only about 9 days in the atmosphere before falling back to Earth as precipitation. 9 days. So the water in the clouds above you right now arrived there very recently. Maybe from an ocean on the other side of the world, carried here by gentle winds, waiting to fall as rain on your garden, your roof, your quiet evening walk. Thunderstorms produce lightning, and water plays a central role in how lightning forms. Inside a large cumulonimbus storm cloud, powerful updrafts carry small water droplets and ice crystals upward, while heavier particles fall downward. These collisions transfer electrical charge. Lighter particles become positively charged and are carried to the top of the cloud, while heavier particles become negatively charged and accumulate toward the bottom. This separation of charge builds up into enormous electrical potential. When the charge difference becomes large enough, electricity discharges, either within the cloud or between the cloud and the ground. The spark of lightning moves at about 1/3 the speed of light and heats the air around it to about 30,000 Kelvin, 5 times hotter than the surface of the sun. All of that because water droplets bumped against ice crystals in the dark heart of a cloud. Fog and clouds are, physically speaking, the same thing. They are both made of tiny water droplets suspended in air. The only difference is altitude. A cloud that forms at ground level, or when a cloud descends low enough to touch the ground, is called fog. Fog forms when air near the surface cools to the point where water vapor condenses into droplets. This often happens on clear, calm nights when the ground loses heat quickly, cooling the air just above it. It happens over rivers and lakes when warm water evaporates into cold air above it. Walking through fog is, in a very real sense, walking through a cloud. Each breath you take on a foggy morning draws tiny water droplets into your nose and lungs. You are breathing cloud. Slowly, gently, the sky comes down to meet you. A rainbow is one of the most gentle, beautiful things that water does with sunlight. When sunlight enters a water droplet in the air, it slows down slightly and bends. This is called refraction. Different wavelengths of light bend by slightly different amounts, spreading the white light into its component colors: red, orange, yellow, green, blue, indigo, violet. The light then reflects off the inside of the droplet and exits, refracted again. When millions of droplets do this all at once, the colors are spread across the sky in a gentle arc. You always see a rainbow with the sun behind you and the rain ahead. The center of a rainbow's arc is actually the anti-solar point, the shadow of your own head. In a very quiet, mathematical way, every rainbow you have ever seen was centered on you. Gently, perfectly centered on you. Now, as we continue, let us move gently downstream. Rivers are one of the most powerful sculptors of the land. Over millions and millions of years, the steady flow of water carves through rock, carries sediment, and shapes the landscape into valleys, canyons, deltas, and plains. The Grand Canyon, one of the most magnificent landscapes on Earth, was carved primarily by the Colorado River over the course of about 5 to 6 million years. Water, which is soft, which yields to your hand when you press against it, has cut through rock that is nearly 2 billion years old. It did this not through force alone, but through patience, endless, quiet, persistent patience. Each drop of water carrying a tiny, almost invisible amount of material downstream. Across millions of years, those tiny amounts add up to something vast. Rivers do not hurry. They simply keep going slowly, gently, endlessly. When a river flows across a flat, gentle landscape, it rarely flows in a straight line. Instead, it develops gentle curves and loops called meanders. These form because as water moves, the fastest moving part of the flow tends to be on the outside of any curve. That faster moving water erodes the outside of the bend, while slower water on the inside of the bend deposits sediment. Over time, these small differences are amplified. Bends get larger and more pronounced. Some meanders become so extreme that the river eventually cuts through the narrow neck of land separating two parts of the bend, creating a curved, isolated lake called an oxbow lake. The river has, in a way, abandoned a piece of itself, left a quiet crescent of still water in the field, separated from the main flow, resting gently in the grass and reeds. The Amazon River in South America is by far the largest river in the world by volume of water. Every second, the Amazon discharges approximately 209,000 cubic meters of water into the Atlantic Ocean. That is more water than the next 7 largest rivers in the world combined. The Amazon drains a basin of about 7 million square kilometers, an area roughly the size of the entire continental United States. The river is so vast that when it enters the Atlantic Ocean, its fresh water can be detected in the ocean hundreds of kilometers from the coast. The Amazon and the forest through which it flows, the Amazon rainforest, together form one of the most important water systems on Earth, cycling water, generating rain, cooling the land. A great, quiet river at the heart of a great, quiet forest. We think of lakes as permanent features of the landscape, but on the timescale of geology, they are temporary. Lakes form when water accumulates in a depression in the land, caused by glaciers carving out basins, tectonic activity creating rifts, or rivers creating oxbows. But lakes are constantly being filled in by sediment carried by their rivers, or drained by rivers cutting through their banks, or evaporated in dry climates. Most lakes are geologically young, thousands to hundreds of thousands of years old. A very few are ancient. Lake Baikal in Siberia is estimated to be 25 to 30 million years old and is by far the world's oldest lake. Most lakes that exist today will be gone in a few million years, silently filled in, transformed into meadows or forests. Temporary resting places for water in the long, long journey of the water cycle. Lake Baikal in Siberia, Russia, is a truly extraordinary body of water. It is the world's deepest lake, reaching a maximum depth of 1,642 meters. It is the world's oldest lake, and it contains approximately 23,615 cubic kilometers of water, which is about 20% of all the surface fresh liquid water on Earth. All the other freshwater lakes in the world combined hold less than Lake Baikal. If you were to drain all the rivers that flow into Lake Baikal and stop all precipitation, it would take approximately 400 years for the lake to empty through its single outflow river, the Angara. The lake sits in a rift valley where two tectonic plates are slowly pulling apart. And Baikal is, in a sense, the beginning of a new ocean, millions of years in the future, quietly opening beneath the cold Siberian ground. And we can take a moment to notice how still and quiet a deep lake can feel. In a deep, calm lake, water naturally arranges itself into distinct layers based on temperature, and this layering is called thermal stratification. Warm water near the surface is less dense and sits on top. Cold water near the bottom is more dense and sinks. Between these layers, there is often a zone called the thermocline, where temperature changes rapidly with depth. In summer, this stratification can be quite strong. The surface water and the deep water become almost separate worlds, with very little mixing between them. Nutrients and oxygen move differently in each layer. Many fish live their lives in one particular zone. In autumn, as the surface cools, the layers mix again in a gentle process called turnover, redistributing nutrients and oxygen throughout the lake. The lake breathes seasonally, quietly, in the rhythm of changing temperatures. Not all rain that falls runs off into rivers and streams. Much of it soaks into the ground, filtering down through layers of soil and rock until it reaches a zone that is already saturated with water. This underground reservoir is called an aquifer, and the water within it is called groundwater. Groundwater moves very slowly, sometimes only a few centimeters per year, through the tiny spaces between grains of soil and through cracks in rock. Eventually it may flow out as a spring, seeping quietly from a hillside into a stream, or it may be drawn up by the roots of trees, or it may remain underground for thousands or even millions of years. Some groundwater currently being pumped up for drinking and farming in dry parts of the world fell as rain during the last ice age, more than 10,000 years ago. Ancient water stored patiently underground. Wetlands, marshes, swamps, bogs, fens, and other areas where the land is saturated with water are among the most biologically productive ecosystems on our planet. They support enormous numbers of species of birds, fish, insects, plants, and other organisms. They filter water, removing pollutants and nutrients as water passes slowly through their dense vegetation and rich soils. They store carbon in the thick layers of organic material that accumulate over centuries in their waterlogged soils. They buffer coastlines against storm surges and flooding. And they are often places of extraordinary quiet and beauty. The sound of frogs at dusk, the slow drift of a heron standing still in shallow water, the smell of green growing things. Half of the world's wetlands have been lost in the last century, and what remains is something quietly precious. In some parts of the world, rivers disappear underground. This happens particularly in karst landscapes, regions underlain by soluble rock like limestone, where acidic rainwater has slowly dissolved the rock over thousands of years, creating caves, tunnels, and vast underground passages. A river can flow on the surface, reach a place where the ground is hollow beneath it, and simply drain away into the rock. Underground rivers can flow for many kilometers through cave systems before emerging at the surface again. Puerto Princesa in the Philippines has an underground river that is nearly 9 kilometers long and navigable for much of that length. Imagine sitting in a small boat in complete darkness, listening to the sound of water flowing through stone tunnels that took thousands of years to form. The river, quiet and invisible, moving through the Earth's own body. A waterfall forms when a river flows over a band of harder rock and then over softer rock, which erodes more quickly, creating a cliff. But waterfalls are not permanent. The rushing water at the base of a waterfall constantly erodes the soft rock at the bottom, undercutting the cliff and causing it to collapse and retreat upstream. Over geological time, a waterfall slowly migrates upstream, eating its way back through the rock. Niagara Falls, for example, has been retreating upstream at a rate of about 1 meter per year for thousands of years. If you could watch it on a geological timescale, you would see the waterfall slowly walking backward up the river. Eventually, thousands or millions of years from now, the falls will have migrated so far upstream that the cliff will have been reduced to a gentle rapid. All that roaring water, quietly making itself disappear, gently moving forward into the world of living things. Your body right now is roughly 60% water. In a person weighing about 70 kilograms, that is approximately 42 liters of water distributed throughout every cell, every tissue, every organ. The percentage varies by tissue type. Blood is about 83% water, muscles about 79%, lungs about 80%, the brain about 73%. Even bones are about 31% water. Water is the medium in which nearly every biochemical reaction in your body takes place. It carries nutrients to your cells and carries waste away from them. It regulates your body temperature through sweating. It cushions your joints. It fills the spaces within and between your cells. When you are fully rested and comfortable right now, all of that water is quietly doing its work, sustaining you, keeping every process running smoothly and gently. Every breath you exhale is humidified by the time it leaves your body. Your lungs are moist surfaces, and the air you breathe out is warm and saturated with water vapor. This is why on a cold day you can see your breath as a little cloud. You are exhaling water. The average person loses about 300 to 400 milliliters of water per day simply through breathing. Without any exercise, without any sweating, just through the normal, gentle, automatic process of breathing in and out. During sleep, as your breathing slows and becomes shallower, you lose water this way more slowly. But still, through the whole night, your body is releasing a little bit of water with each quiet exhale. Your breath going out into the room, a thin mist of water leaving you in the dark. A large tree, in the heat of summer, can pull several hundred liters of water up from the soil through its roots, up through its trunk and branches, and out through the tiny pores on its leaves every single day. This process is called transpiration, and it is driven not by any pump or mechanical force, but by the simple evaporation of water from the leaf surface. As water evaporates from the leaves, it creates a gentle tension in the water column inside the tree, like drinking through a very long straw that pulls more water up from the roots. The water columns inside a tree can experience tension strong enough to pull water to the tops of the tallest trees, more than 100 meters above the ground. All of this quietly inside the tree, all day long, driven by nothing more than the sun and the gentle pull of evaporation. One of the most important chemical reactions on Earth is photosynthesis, the process by which plants, algae, and some bacteria use sunlight to make food. And water plays a essential role. During photosynthesis, a plant absorbs water through its roots and carries it up to its leaves. In the leaves, a tiny but extraordinary event takes place. Sunlight energy is used to split water molecules apart. The hydrogen atoms from the water are used to build sugars. The oxygen atoms are released into the air, and that released oxygen is what fills our atmosphere, what you are breathing right now. The oxygen you are breathing in this moment, was once part of a water molecule. A plant separated it from its hydrogen and released it into the world for you to breathe. Jellyfish are among the most water-dominated creatures on Earth. The body of a jellyfish is approximately 95 to 98% water. They have no brain, no heart, no bones, no blood. Their body consists of a simple gelatinous substance called mesoglea, sandwiched between two thin layers of cells, all of it mostly water. And yet they move, they react, they catch food, they reproduce, they have survived for hundreds of millions of years. They are among the oldest multicellular animals on Earth, predating the dinosaurs by many hundreds of millions of years. Some species are bioluminescent, glowing gently in the dark ocean. They drift with the currents, pulsing slowly, almost entirely transparent, almost entirely water, quietly ancient in the quiet sea. And we can take a moment to notice the stillness of deep water. Tardigrades, sometimes called water bears, are tiny microscopic animals, about 0.5 millimeter long, that live in thin films of water on mosses, lichens, and other damp surfaces. When their water dries up, they can perform one of the most extraordinary feats in all of biology. They draw their legs inside their body, lose nearly all their body water, and enter a state called cryptobiosis, a kind of suspended animation. In this dried, shrunken, dormant form, they can survive temperatures from near absolute zero up to 150 degrees Celsius, pressures 6 times greater than the deepest ocean trench, high doses of radiation, and even the vacuum of outer space. They can stay in this dormant state for decades. Then, when water returns, they slowly rehydrate, their legs extend, and they walk and eat and live again. Water, bringing life back from a state almost indistinguishable from death. Fish can sense water movement around them in a way that we cannot, through a special sensory system called the lateral line. This is a series of tiny sensory organs arranged in a line along each side of a fish's body, running from just behind the head to the tail. These organs detect vibrations and pressure changes in the surrounding water. The movement of other fish nearby, the reflected pressure waves bouncing back from obstacles, the tiny disturbances made by prey moving in the water. It is, in some ways, like a kind of touch sense that extends beyond the fish's body, out into the water around it. Schools of fish use their lateral lines to coordinate their movements with extraordinary precision. Thousands of fish turning and banking together in response to each other's wake, like a living, silver, fluid ribbon moving through the water. Frogs do not drink water through their mouths. They absorb water directly through their skin, which is thin, moist, and highly permeable. Water moves through the skin by osmosis, from the wetter environment into the frog's body. Frogs also absorb oxygen through their skin, which is why they must always keep it moist. If a frog's skin dries out, it can no longer breathe or stay hydrated, and it will die. Some desert frogs have a specially absorbent patch of skin on their undersides called the drinking patch. To rehydrate, they simply sit in a puddle and let water soak through. The entire act of drinking happens silently, through the skin, without opening a mouth. Water quietly absorbed from the wet ground into the living body. Large forests, particularly tropical rainforests, are capable of generating their own rainfall. Through transpiration, the billions of trees in a forest release enormous quantities of water vapor into the air above them. This water vapor rises, cools, condenses, and falls back as rain. Some studies suggest that as much as half of the rainfall in the Amazon basin is generated by the forest itself, recycled from the previous day's transpiration. The forest breathes water out, and the sky breathes water back. Scientists have called these invisible rivers of moisture in the air flying rivers, and they can carry as much water as major physical rivers. When large areas of forest are cleared, these flying rivers weaken, and rainfall in and around the deforested areas can decline significantly. The forest makes its own rain. The trees water themselves. Your kidneys are extraordinary water managers. Every day, your 2 kidneys filter approximately 180 liters of fluid. That is nearly twice your own body weight in fluid passing through the kidneys each day. Of that 180 liters, all but about 1.5 to 2 liters is reabsorbed back into the bloodstream, carefully processed and recycled. Only the waste products and excess water are released as urine. The kidneys are constantly regulating the water balance of your body, adjusting how much water you retain or release in response to how much you have drunk, how much you have sweated, what you have eaten. Right now, while you rest, your kidneys are doing this work quietly, gently, without any conscious effort on your part. Your body managing its water all night long. Now, as we continue, let us think about water and the human world. Every major ancient civilization developed along a river. The Egyptians along the Nile, the Mesopotamians along the Tigris and Euphrates, the Indus Valley civilization along the Indus River, the Chinese civilization along the Yellow River. This is not a coincidence. Rivers provided everything that early human settlements needed: fresh water for drinking, water for growing crops, fish for eating, fertile soil deposited by seasonal floods, and transport routes. The regular flooding of rivers like the Nile brought rich silt down from upstream, depositing it on the fields along the riverbanks and making the land extraordinarily fertile. People built their lives along these rivers, and their cities, their religions, their entire cultures grew from the relationship between people and water. The river was not just part of life. For many ancient peoples, the river was life itself. The ancient Romans understood the importance of water and built extraordinary systems to bring it to their cities. At the height of the Roman Empire, the city of Rome was served by 11 major aqueducts, which together carried approximately 1 million cubic meters of water per day into the city, roughly 1,000 liters per person. The aqueducts were built with incredible precision, constructed at a very gentle, carefully calculated slope, so that water would flow by gravity alone, without any pumps. Some of these aqueducts were dozens or hundreds of kilometers long. Portions of several Roman aqueducts still stand today, nearly 2,000 years later. Massive stone structures stretching across the Italian countryside, a testament to how seriously the Romans took the question of water. They built their civilization, in part, around the engineering of water. The water that comes out of a tap in most modern cities has gone through an elaborate, multi-step purification process before it reaches you. It begins at a source, a river, lake, or reservoir. It is first passed through screens to remove large debris. Then chemicals are added to cause small particles to clump together and settle out, a process called coagulation and flocculation. The water is then filtered through layers of sand, gravel, and sometimes activated charcoal. Disinfectants, usually chlorine or chloramine, are added to kill any remaining bacteria and viruses. The water is tested at many points along the way. By the time it reaches your tap, it has been carefully cleaned and monitored to be safe to drink. The casual act of turning on a tap and receiving clean water is the end result of a very careful, very quiet process of science and engineering. Before electrical refrigeration existed, people in many parts of the world used snow and ice to preserve food. Ice was cut from frozen rivers and lakes in winter and stored in insulated underground pits called ice houses, packed in sawdust or straw, where it could last well into summer. Ice was also transported long distances. In the 19th century, the United States had a significant industry of cutting and shipping natural ice from New England to warmer parts of the country, and even abroad to places like India. Ice would be cut in large blocks, packed in insulating material, loaded onto ships, and transported across the ocean, arriving with much of the original ice still intact. This was water in its solid form, being used as a tool by human civilization, harvested, stored, traded, and depended upon. Long before mechanical clocks, water was used to measure the passage of time. A clepsydra, from the Greek meaning water thief, is a water clock, one of the oldest known timekeeping devices. A simple version consists of a container with a hole in the bottom. As water drains out at a controlled rate, the falling water level marks the passage of time. More sophisticated versions use the rising water level in a receiving container to move a float, which turned a pointer on a dial. Water clocks were used in ancient Egypt, Mesopotamia, Greece, and China thousands of years ago. The steady, predictable flow of water, something that runs reliably, that cannot be hurried or slowed, that moves at a constant pace when undisturbed, made it a natural medium for measuring time. Water as clock, the flow of water as the flow of time. Let's take a quiet moment to think about the steady sound of flowing water. In the morning, after a cool, clear night, you often find surfaces covered in tiny drops of water. On grass, on leaves, on car windows, on spider webs. This is dew, and it forms through a very simple process. During the night, the ground and surfaces on it radiate heat away into the clear sky and cool down. When these surfaces cool to a certain temperature called the dew point, the water vapor in the air directly touching those surfaces condenses into liquid droplets. The dew forms quietly while you sleep. By morning, every blade of grass holds its own small jewel of water, and spider webs that were invisible in the dry afternoon are suddenly outlined in 100 tiny spheres of light. Then, as the sun rises and the air warms, the dew evaporates again, rising invisibly back into the atmosphere. Water appearing and disappearing with the turning of the day. Long before electricity was discovered, water was used to power machines. Water wheels, large wooden wheels turned by the flow of a river, were used in ancient Rome to grind grain into flour. In the medieval period, water mills spread across Europe, powering not just grain mills but also sawmills, textile mills, forge hammers, and many other machines. The kinetic energy of flowing water, converted into the rotation of a wheel, could do work that would otherwise require the labor of many people or animals. Today, hydroelectric dams use the same basic principle at a vastly larger scale, using the flow of water through turbines to generate electricity. Approximately 16% of the world's electricity currently comes from hydropower. The same energy that has been turning wheels since ancient Rome, now quietly lighting cities and charging devices all around the world. Pure water is not completely colorless, even though it appears that way in small quantities. In very large volumes, pure water has a faint but real blue color. This is because water molecules absorb red light wavelengths more strongly than blue wavelengths. In deep, clear ocean water, or in deep swimming pools, this natural blue absorption becomes visible. The blue color of the deep ocean is partly a reflection of the blue sky, but partly the true color of the water itself. In very clear, deep waters like those of Lake Baikal or the Pacific Ocean far from any coast, the blue can be intensely beautiful, a deep, rich, vivid blue that seems to glow. That color is simply physics. Simply the way water interacts with light. And it is, in its quiet way, one of the most beautiful colors in the world. When water seeps into cracks in rock and then freezes, it expands, increasing in volume by about 9%. This expansion exerts an enormous pressure on the surrounding rock, up to 2,000 atmospheres in some conditions. Over time, with repeated freezing and thawing, this pressure can split the rock apart. This process, called frost weathering or freeze-thaw weathering, is one of the primary ways that rock is broken down into the smaller pieces that become soil. It is how mountain peaks are slowly broken and rounded. It is how potholes form in roads. Water, quietly, patiently, freezing and expanding in a crack no wider than a hair, exerting pressure year after year after year, until the rock yields. The soft, patient persistence of water, reshaping the hard world. Scientists have discovered water deep underground that has been completely sealed off from the surface for extraordinarily long periods of time. In mines in Canada and South Africa, water has been found in deep rock fractures that has been isolated from the surface for more than 1 billion years. This water was analyzed using geochemical techniques and found to be ancient beyond imagination, sealed in rock since long before complex life existed on Earth. It contains gases and chemical signatures that testify to its extraordinary age. Water that has been sitting completely undisturbed in a crack in the rock, since before there were any fish in the ocean, before there were any animals at all on land, before almost anything alive today existed on this planet. Ancient water, waiting, quiet, patient beyond all comprehension, gently moving forward into the quiet body. Your brain and spinal cord float in a clear fluid called cerebrospinal fluid, which is about 99% water. This fluid circulates slowly around the brain and spinal cord, providing a liquid cushion that absorbs shocks, delivering nutrients and removing waste products. It is produced continuously in specialized structures within the brain called the choroid plexus, circulates gently around the brain and down the spinal cord, and is then absorbed back into the bloodstream. Your brain essentially floats in this fluid. If it were not there, the brain would rest against the inside of the skull under its own weight, which would damage it. Right now, as you rest, as your brain does its quiet nighttime work, it floats gently in its clear, warm, watery cushion. Protected, cradled, softly held. In 2013, scientists discovered something remarkable about what happens in the brain during sleep. The glymphatic system, a network of channels around the brain's blood vessels, becomes significantly more active during sleep, allowing cerebrospinal fluid to flow through the brain more vigorously and flush out metabolic waste products, including proteins linked to neurological diseases. It is as though the brain has its own nightly cleaning cycle, powered by water. While you sleep, fluid moves through the spaces between cells, carrying away the biochemical debris that accumulated during the day. This is one of the most important functions of sleep, and it relies entirely on the movement of water through the brain's tissues. As you drift towards sleep, your brain is preparing for this quiet, watery cleansing. The water in your brain, doing its most important work in the dark. Blood is approximately 55% plasma, and plasma is approximately 92% water. So blood, the fluid that carries oxygen and nutrients to every cell in your body and removes waste from every cell, is largely water. The water in your blood is the medium in which red blood cells travel, in which dissolved oxygen is carried from the lungs to the tissues, in which glucose and amino acids and minerals are transported to wherever they are needed. The blood in your body right now is moving quietly through your arteries and veins, doing all of this work at every moment. Your heart beats about once per second, pushing that watery blood through approximately 100,000 kilometers of blood vessels, enough to circle the Earth 2.5 times. All of it moving quietly, powered by your heart through the night. Tears are not simply water. They are a carefully formulated liquid produced by the lacrimal glands near the eye, containing water, electrolytes, proteins, lipids, and various other molecules. There are 3 distinct types of tears. Basal tears are produced continuously to keep the eye moist and are essential for clear vision and eye health. Reflex tears are produced in response to irritants, smoke, onions, foreign objects. Emotional tears are produced in response to strong feelings and have a slightly different chemical composition from reflex tears, including higher concentrations of proteins and stress hormones. The act of crying emotional tears may actually help the body remove stress-related chemicals. Your tears are a small, precise, chemically sophisticated version of the ocean, salty water, carefully formulated, released by the body in its most feeling moments. Your body regulates its temperature in part through sweating. When your body temperature rises, through exercise, hot weather, fever, sweat glands in your skin produce a watery solution that rises to the surface of the skin. As this water evaporates from your skin's surface, it carries heat away with it. This is the same principle that makes you feel cooler when you step out of a pool on a windy day. The evaporation of water requires energy in the form of heat, and that heat comes from your body. This is why evaporating sweat cools you. The water takes your heat with it as it leaves. The human body can produce several liters of sweat per hour during intense exercise in the heat, and this evaporative cooling is so effective that humans are among the best long-distance runners in the animal kingdom. Water, cooling us from the outside in. There is no need to rush, we can stay here gently for a while. Even mild dehydration, losing just 1 to 2% of your body's water, can measurably affect cognitive function. Studies have shown that even slight dehydration can impair concentration, memory, and mood. The brain is about 73% water, and its biochemical processes depend on adequate hydration. When you are well hydrated, neurotransmitters move efficiently, neural signals travel smoothly, and thinking feels clear and easy. When you are dehydrated, those same processes slow down slightly, and thinking can feel foggy, slow, and difficult. Drinking a glass of water when feeling mentally sluggish is often genuinely helpful, not just a placebo. Your brain, like every other part of your body, runs on water. And right now, as your body is at rest, your brain is working with the water it has quietly and efficiently, doing the deep and mysterious work of sleep. Specific heat is a measure of how much energy it takes to raise the temperature of a substance by 1 degree. Water has an extraordinarily high specific heat compared to most other substances. This means water can absorb a large amount of heat without changing its temperature very much. And conversely, it can release a large amount of heat as it cools without dropping in temperature very quickly. This property is enormously important for life. Because our bodies are mostly water, our body temperature stays relatively stable even when we are exposed to varying amounts of heat or cold. The water in our cells acts as a thermal buffer, absorbing or releasing heat slowly, keeping our internal temperature within the narrow range in which our biochemistry can function. The same property makes the ocean a global temperature moderator. Water resisting change, stabilizing things quietly and steadily. Human babies are born with a higher proportion of water in their bodies than adults. A newborn baby is approximately 78% water. As we age, that percentage decreases to about 65% in childhood and settling to around 60% in adults. Some of the difference is in the distribution of water. Newborns have relatively more water in the fluid spaces between their cells, and their cells themselves are relatively more hydrated. The high water content of infants is connected to their rapid growth and development. Cells need water to divide and grow, and a developing body uses water in enormous quantities. As the body matures and the proportion of denser tissues like bone and muscle increases, the overall water percentage decreases. We begin life mostly water. Soft, new, and mostly water. Inside your eye, the space between the cornea, the clear front surface, and the lens is filled with a clear, watery fluid called the aqueous humor. This fluid maintains the pressure inside the eye, nourishes the cornea and lens, which have no blood supply, and plays a role in the eye's optical properties. It is produced continuously by a structure called the ciliary body and drains out through a tiny channel called the trabecular meshwork. A very small imbalance between production and drainage can raise eye pressure, which is associated with the condition called glaucoma. Behind the lens, a larger cavity is filled with a clear, gel-like substance called the vitreous humor, which is about 98% water. Your eyes are held in shape, nourished, and made optically clear by water. Right now, behind your closed eyelids, your eyes rest in their quiet, watery chambers. The nervous system sends signals through electrical impulses, and water is essential to how this works. Nerve signals are generated by the movement of charged ions, sodium, potassium, calcium, chloride, across the membranes of nerve cells. These ions move through water-filled channels in the cell membrane, driven by concentration gradients and electrical potential. The whole system depends on water as the medium in which these ions are dissolved and through which they move. Without the water in and around your nerve cells, there would be no ionic gradients, no movement of charge, no electrical signals, and no nervous system function at all. Every thought you have ever had, every movement, every sensation, every dream, all have been carried on electrical signals that depend on water, the soft, quiet medium through which your mind moves. Now, as we continue, let us travel to some of the more unusual places water can be found. Water is not just found on Earth. It exists throughout the universe. Radio telescopes have detected water vapor in clouds of gas and dust between stars in the interstellar medium. In fact, water is one of the most common molecules in the universe. Giant clouds of water vapor surround some types of stars. Water ice coats the surfaces of dust grains drifting through space. It exists in the atmospheres of some planets and moons in our solar system. A particularly spectacular example. Astronomers have detected a cloud of water vapor around a quasar, an incredibly bright, ancient cosmic object, about 12 billion light-years away. The amount of water in that cloud is estimated to be 140 trillion times the amount of water in all of Earth's oceans. Water, in unimaginable quantities, floating in the darkness between the stars, waiting, perhaps, for a planet to form around it. Mars today is cold, dry, and apparently barren. Its surface is swept by dust storms, its atmosphere is thin, and there is no liquid water on its surface. But billions of years ago, Mars was very different. Evidence from spacecraft and rovers has shown that water once flowed across the Martian surface. We can see the dried riverbeds, the ancient shorelines, the minerals that only form in the presence of liquid water. For hundreds of millions of years, Mars may have had a warmer, wetter climate with rivers, lakes, and perhaps even shallow seas. What happened to all that water is still being studied, but much of it is believed to have been lost to space as the planet lost its magnetic field and its atmosphere thinned. The rest may be frozen in the polar ice caps or locked deep underground. A once wet world, slowly dried, slowly stilled. One of the most exciting places in the solar system is Europa, a moon of Jupiter slightly smaller than our own moon. Europa is covered in a thick shell of ice, but beneath that ice, scientists believe there is a global ocean of liquid water. The evidence comes from the moon's complex, fractured ice surface, which looks as though something is moving beneath it, and from measurements of its magnetic field, which suggest a conducting liquid interior. The ocean is kept liquid by tidal heating. The gravitational pull of Jupiter's enormous mass flexes Europa as it orbits, generating heat through friction, just as squeezing a rubber ball repeatedly makes it warm. If Europa does have a liquid ocean, it may be one of the best places in the solar system to look for extraterrestrial life. Life, perhaps, in a vast dark ocean under kilometers of ice, around a distant frozen moon. Even more dramatic than Europa, Saturn's moon Enceladus has been observed to actively spray water into space. The Cassini spacecraft, which orbited Saturn for 13 years, flew directly through the plumes of water vapor and ice particles erupting from cracks near Enceladus's south pole. These plumes contain not just water, but also organic molecules, silica, hydrogen, and other chemical signatures. The interior of Enceladus appears to harbor a warm, liquid water ocean in contact with a rocky seafloor. Conditions that some scientists consider favorable for life. Water from Enceladus's ocean is literally being sprayed into space, where it forms one of Saturn's rings. Some of that water has been collected by a spacecraft and analyzed in a laboratory on Earth. Water from inside an ice moon of Saturn, studied by human beings. The journey of water extended to the edges of the solar system. Our own moon is far too cold in permanently shadowed regions to ever receive direct sunlight. In the deep craters near the moon's north and south poles, temperatures stay perpetually near -250 degrees Celsius. And in those frozen, sunless places, scientists have detected water ice. It likely arrived there over billions of years via comets and asteroids, and once in the permanent shadow of the polar craters, it was frozen in place indefinitely. Some estimates suggest there may be billions of tons of water ice at the moon's poles. This discovery is significant for the future of space exploration. Water on the moon could be used by future astronauts as drinking water and could be split into hydrogen and oxygen to make rocket fuel. The water that once arrived on the moon from a comet, waiting in a cold, dark crater for a very long time, perhaps soon to be used by humans in the next chapter of exploration. And we can take a moment to notice the incredible reach of water to every corner of the solar system. Under the vast, thick ice sheet of Antarctica, scientists have discovered more than 400 subglacial lakes, liquid water trapped beneath kilometers of ice in complete darkness. The water is kept liquid partly by the pressure of the overlying ice, which lowers the melting point of ice, and partly by heat seeping up from the Earth's interior. The largest of these, Lake Vostok, is the size of Lake Ontario and has been isolated from the atmosphere for somewhere between 15 and 25 million years. The lake contains life. Bacteria have been found in ice cores drilled from just above the lake, suggesting that life may persist in the lake itself. Life in a dark, cold, ancient, isolated lake under kilometers of ice. Water that has been undisturbed since before our human ancestors walked the earth, harboring quiet, ancient life. The Atacama Desert in Chile is one of the driest places on Earth. Some parts of the Atacama receive essentially no rain at all, year after year. And yet, life exists there. Near the Pacific coast, fog frequently rolls in from the ocean, even where it almost never rains. Some plants have evolved to collect this fog water directly from the air. Their leaves and branches are covered in fine hairs or waxy structures that trap tiny fog droplets and direct them down to the roots. Engineers have been inspired by these plants to create fog collectors, large mesh nets that trap fog droplets and collect the water, providing drinking water in communities where rain never falls. The desert taking its water not from the sky, but from the air itself, from the fog that rolls in from the sea, soft and silent in the early morning. The Namib Desert of Africa is another extremely dry place, but certain beetles that live there have evolved a remarkable strategy for collecting water. At dawn, fog rolls in from the Atlantic Ocean over the desert. The fog beetle climbs to the top of a sand dune, faces into the wind, and tilts its body forward at an angle. Its back surface has a microstructure of tiny bumps, hydrophilic tips that attract water, surrounded by hydrophobic areas that repel it. Fog droplets land on the tips of the bumps, grow, and when large enough, roll down along the water-repelling surfaces toward the beetle's mouth. It drinks. This structure on the beetle's back has inspired materials scientists to design new types of surfaces and materials for water collection, water filtration, and anti-icing applications. Nature had already solved the problem, quietly, millions of years ago. A geyser is a hot spring that periodically erupts jets of hot water and steam into the air. They form in regions of volcanic activity, where groundwater seeps down through rock that is heated by magma below. The key to a geyser is its particular underground structure, a long, narrow tube or series of chambers that acts like a pressure cooker. Deep underground, the water is under enough pressure that it can be heated far above the normal boiling point of 100 degrees Celsius without turning to steam. As heat builds up, the water at the bottom begins to boil, reducing the pressure above it, which allows the water above it to flash instantly into steam. This creates a chain reaction. Steam surges up through the column of water, and the geyser erupts. Old Faithful in Yellowstone erupts approximately every 90 minutes, reliably, steadily, water heated by the Earth's own heat. Under certain conditions, water can remain liquid even at temperatures below 0 degrees Celsius. This is called supercooling. It happens when water is very pure and the cooling happens very slowly, with no surfaces or particles that could act as nucleation sites for ice crystals to form. Supercooled water can stay liquid down to about minus 40 degrees Celsius. In clouds, small droplets of very pure water are often supercooled, remaining liquid even though they are well below freezing. When these supercooled droplets hit a surface, they instantly freeze on contact, a process called freezing rain or icing. Aircraft are particularly vulnerable to this. Supercooled droplets can coat wings with ice almost instantly. Water patiently refusing to freeze, maintaining its liquid form past the temperature at which it should have already changed. Gently moving forward into the quiet world of water's physics. We touched on this earlier, but it is worth returning to gently. In almost every other substance we know, the solid form is denser than the liquid form. The molecules in a solid are more tightly packed, so solids usually sink in their own liquid. But water is different. When water freezes, its molecules form a crystal lattice with gaps in it, a more open, less dense structure than liquid water. So ice floats. This is what we call an anomalous property. And as we mentioned, this anomaly is essential for aquatic life. But it also has consequences for geology. The expansion of water as it freezes is what breaks rocks, what carved the landscapes of Earth during the ice ages, what created the soils in which our food grows. This one quiet anomaly, this gentle exception to the rule, shapes the world we live in. Water molecules have a strong attraction to each other, a property called cohesion, and this is what allows water to form droplets. When water falls or drips from a surface tension pulls the water into the smallest possible shape, a sphere. When you watch water dripping from a faucet in slow motion, you can see each droplet form, stretch, and separate in a beautiful, fluid sequence. The drop forms, elongates as gravity pulls it down, necks in the middle, and then separates. The surface tension snapping the connection and forming two separate water masses, each immediately rounding into the most perfect sphere it can manage. That roundness is the result of millions of water molecules all pulling equally on each other, reaching a peaceful equilibrium. The physics of attraction, the geometry of peace. This is one of the most counterintuitive and debated observations in the behavior of water. Under certain conditions, hot water can freeze faster than cold water. This is known as the Mpemba effect, named after a Tanzanian student, Erasto Mpemba, who observed it while making ice cream and brought it to the attention of scientists in the 1960s. The effect does not always occur. It depends on the specific conditions, the containers, whether there is evaporation, whether the water contains dissolved gases. Scientists have proposed various explanations involving evaporation, convection currents, dissolved gases, and the behavior of hydrogen bonds. The Mpemba effect remains an active area of research. It is a reminder that even something as familiar as the freezing of water still holds quiet mysteries, things science is still gently untangling. If you look at the molecular weight of water, how heavy its molecules are, you would expect it to boil at around minus 80 degrees Celsius. Molecules of a similar size and weight boil at temperatures far below zero. But water actually boils at 100 degrees Celsius, a full 180 degrees higher than you might expect. The reason is hydrogen bonding. The water molecule's unique shape and electrical asymmetry allows each water molecule to form hydrogen bonds with up to 4 neighboring water molecules. These bonds are weak individually, but there are so many of them that they hold water molecules together much more strongly than their size would suggest. Breaking those bonds, which is what happens at boiling, requires significantly more energy than breaking the van der Waals forces that hold simpler molecules together. This higher than expected boiling point is, again, one of the reasons liquid water exists on Earth's surface and makes life possible. Closely related to its high boiling point is water's very high latent heat of vaporization. the amount of heat energy required to turn liquid water into water vapor at the same temperature. This value for water is about 2,260 joules per gram. That is a very large amount. It means that even after water reaches 100 degrees Celsius, you must add a great deal more energy to actually turn it into steam. This high latent heat is why a burn from steam is much more severe than a burn from water at the same temperature. The steam carries far more stored energy that it releases as it condenses on your skin. And at a planetary scale, this high latent heat is one of the reasons the water cycle moderates Earth's climate. Enormous amounts of solar energy are absorbed and released as water evaporates and condenses, rather than directly heating the air. Now, as we continue, let us hold these ideas gently. There is no need to understand everything, just to rest with these ideas. Despite being a liquid, water is nearly impossible to compress. If you apply pressure to water in an enclosed container, its volume barely changes at all. This is why hydraulic systems work. A force applied to water at one end of a closed tube is transmitted almost perfectly to the other end, without the water compressing and absorbing the force. Car brakes, hydraulic lifts, and heavy construction machinery all rely on this property of water. The incompressibility of water is also why a belly flop into a pool can hurt. At high impact speed, the water does not compress or give way, and the force of impact is almost fully transmitted back to the body. And deep in the ocean, despite the enormous pressure, 1,000 times atmospheric pressure at the deepest trenches, water is only about 5% more dense than it is at the surface. Water holds its shape quietly under immense force. Pure water, in isolation, is actually a very poor conductor of electricity. The water molecules themselves do not carry charge. But water is almost never truly pure. It almost always has dissolved minerals and salts in it, and those dissolved ions are what conduct electricity. Tap water conducts electricity moderately well because of its dissolved minerals. Seawater is an even better conductor because of its high salt content. The tiny electrical conductivity of even very pure water is due to the self-ionization of water. A small number of water molecules at any given time are spontaneously breaking apart into a hydrogen ion and a hydroxide ion, both of which can carry charge. This self-ionization is described by the pH scale. Pure water, at 25 degrees Celsius, has a pH of 7. Neutral. Balanced. A quiet equilibrium between acid and base. The sound of rain, flowing water, and ocean waves is broadly reported to be calming, and there is neurological evidence for this. These sounds are a form of pink noise. Noise that has more energy at lower frequencies than at higher ones, creating a soft, even sound rather than a sharp or harsh one. Pink noise has been shown in several studies to slow brain wave activity, promoting relaxation and easier sleep onset. Some researchers believe that humans may have an evolved association between the sound of flowing water and safety. Water means life, and its sound may signal a safe, resource-rich environment. Others focus purely on the masking effect, where the steady sound blocks out sharper, more alerting sounds from the environment. Whatever the reason, the sound of water is one of the most universally soothing things we know, and we can take a moment to imagine it now. Sunlight can purify water. A simple technique called solar disinfection, SODIS, involves filling clear plastic bottles with contaminated water and leaving them in direct sunlight for 6 to 8 hours. The ultraviolet radiation in sunlight damages the DNA of bacteria and viruses in the water, rendering them unable to reproduce and killing them. This technique has been promoted in parts of the developing world as a low-cost way to purify drinking water. On a larger scale, industrial water treatment systems use powerful UV lamps to disinfect water without adding chemicals. The sun, which is ultimately the energy source for almost all life on Earth, can also kill microorganisms in water. Light and water working together to make water safe. The same sunlight that makes rain clouds through evaporation, that powers photosynthesis, also quietly disinfects. In very narrow tubes, water can rise upward against the force of gravity without any pump or pressure. This is called capillary action, and it is the result of the combination of water's adhesion to surfaces and its cohesion to itself. Water molecules cling to the walls of a narrow tube, pulling themselves up the tube wall, and the cohesion between water molecules pulls the rest of the water column along behind them. The narrower the tube, the higher the water can rise. This is how plants draw water upward through their xylem tissue, tiny narrow tubes inside the stem through which water climbs from roots to leaves. It is also why a paper towel soaks up water, why candle wicks work, and why wet sand feels firm to walk on. The capillary attraction between sand grains and water helps to hold everything together. Water rising quietly against gravity through the willingness of molecules to cling. Now, as we continue into the quietness of geological time, a glacier is formed when snow accumulates faster than it melts, year after year. The deep snow at the bottom is compressed by the weight of snow above it, slowly transforming into ice. Over time, the accumulated mass of ice becomes so thick that it begins to flow under its own weight. Very slowly, perhaps a few centimeters to a few meters per day. Glaciers flow downhill, carving U-shaped valleys, grinding rock into powder, carrying enormous boulders far from where they originated. They are like rivers of ice, moving so slowly that from a human perspective they appear perfectly still. But over centuries and millennia, they reshape entire mountain ranges. The rocks scored and polished by ancient glaciers still record the direction of that long, slow flow, scratched into stone by ice that has long since melted and returned to the sea. The Earth has been through many glacial periods, ice ages, over the past several million years, during which large portions of the northern hemisphere were covered by thick ice sheets. The most recent of these ended approximately 12,000 years ago, at the start of the current warm period we call the Holocene. At the peak of the last ice age, around 20,000 years ago, ice sheets covered much of North America, Northern Europe, and parts of Asia. So much water was locked up in ice that sea levels were roughly 120 meters lower than they are today. Entire regions now under the ocean were dry land, including the land bridge between Asia and North America that humans may have crossed to populate the Americas. As the ice melted over thousands of years, the meltwater poured into the oceans, raising sea levels slowly and flooding coastal regions. In limestone caves, dripping water creates one of nature's most patient and beautiful forms of art. As rainwater soaks through the soil and into the limestone rock, it picks up carbon dioxide and becomes mildly acidic, dissolving tiny amounts of the calcium carbonate in the limestone. When this calcium-laden water drips into a cave and is exposed to the cave air, some of its carbon dioxide escapes, and the calcium carbonate precipitates out of solution and deposits as a tiny crystal of calcite. A stalactite forms when these deposits accumulate on the ceiling, hanging down, built drop by drop over thousands of years. A stalagmite forms on the floor beneath, from drops that fall and deposit there. Some cave formations are hundreds of thousands or millions of years old, built at rates of less than a millimeter per year. The slowest, most patient art. Water building stone from stone. The water in any given cloud is not sitting there waiting patiently. It is constantly being replaced. Water droplets in a cloud are evaporating and recondensing continuously, and the cloud as a whole is constantly exchanging water with the surrounding atmosphere, losing droplets at its edges as they evaporate, gaining new droplets as water vapor condenses at its core. The actual lifetime of any individual droplet in a cloud is quite short. The cloud itself may persist for hours or days, but the water inside it is turning over continuously. In some ways, a cloud is like a river, a form that persists while the material flowing through it constantly changes. Or like a flame, which remains while the wax and air that feed it continuously change. The form holds while the substance flows through it. A cloud is a pattern, not a thing. Mineral springs, natural springs with high concentrations of dissolved minerals, often contain water that has been on a long underground journey. Rain falls on the surface, soaks into the ground, and travels slowly downward through rock layers, sometimes descending kilometers into the earth before being forced back upward by geological pressure. Along the way, it dissolves minerals from the surrounding rock: silica, calcium, magnesium, iron, sulfur, and others. When this mineral-rich water emerges at a spring, it carries all of those minerals with it. The temperature of some mineral springs reflects how deep the water traveled. Geothermal heat increases with depth, and deeply circulated water emerges warm or hot. People have valued mineral springs for thousands of years, drinking their waters for health and bathing in them for relaxation. The Earth's deep water, rising slowly, warm and mineral-laden, back into the light. Slowly, gently, the water always returns. Water reaches its maximum density not at 0 degrees Celsius, but at 4 degrees Celsius. As water cools from room temperature toward 0, it first becomes denser, as you would expect, until it reaches 4 degrees. But then, between 4 degrees and 0, something unusual happens. The water becomes less dense again as it approaches freezing, because the water molecules begin to arrange themselves into the hexagonal lattice of ice even before they actually freeze. This means that in a lake cooling in winter, the densest water, at 4 degrees, sinks to the bottom, while the colder water above it stays on top until it freezes. The bottom of a winter lake sits at about 4 degrees Celsius, even when the surface is frozen solid. And that 4-degree bottom layer, through the whole winter, remains liquid. The fish shelter there. Life continues, because of a small, gentle quirk at 4 degrees. A whirlpool is a swirling body of water formed when two currents of water meet and create a rotating motion. Small whirlpools form in rivers wherever water flows around an obstacle or meets a countercurrent. Larger whirlpools form in the ocean where tidal currents interact with headlands or underwater topography. The most powerful permanent whirlpools on Earth, like the Saltstraumen in Norway, are driven by the enormous volume of water that must pass through a narrow strait twice a day with each tide. The water spinning in a whirlpool follows the same spiral pattern found throughout nature. In galaxies, in weather systems, in the shells of snails, in the arrangement of seeds in a sunflower. The spiral of water finds its echoes in the spiral of the universe. The same mathematics, quiet in the water, written large in the cosmos. In strict technical terms, water always flows downhill. Gravity ensures that. But rivers can appear to flow uphill in certain situations. If a strong wind is blowing against the current of a river near its mouth, it can push a wave of water upstream, temporarily reversing the surface flow. This is called a tidal bore, a wave that travels upstream when the incoming tide is strong enough. The Qiantang River in China has one of the world's most spectacular tidal bores, where a wall of water can reach several meters in height and travels upstream at speeds of up to 40 kilometers per hour. A river for a few minutes flowing backward. Water pushed uphill by the tide and the wind. The rules of water, temporarily and gently set aside by the forces of moon and wind. Water is not only found on planets and moons. It is found inside meteorites, the rocky fragments from space that occasionally fall to Earth. Some types of meteorites, called carbonaceous chondrites, contain water in the form of hydrated minerals. Minerals that have incorporated water molecules into their crystal structures during chemical reactions that took place long ago in the early solar system. These meteorites are among the oldest objects we can directly study. Some are more than 4.5 billion years old, older than the Earth. The water in them was present in the asteroid belt from which they came, preserved in mineral form for billions of years, traveling through space and eventually landing on Earth. When we analyze these meteorites in laboratories, we can extract and measure that ancient space water. Water from before the Earth existed, held in stone, arriving as a gift from space. The smell you notice when rain begins to fall on dry Earth has a specific name: petrichor. It was coined in 1964 by two Australian scientists, Isabel Joy Baer and Richard Thomas. The smell comes primarily from a combination of sources. One is geosmin, a compound produced by soil bacteria called actinomycetes, which is released when raindrops disturb the soil. Another is an oil produced by plants during dry periods that accumulates in the soil and rocks and is released when rain falls. A third contribution comes from ozone, produced by lightning during thunderstorms. Humans are extraordinarily sensitive to geosmin. We can detect it at concentrations of just a few parts per trillion. This extreme sensitivity may reflect a deep evolutionary association with rain as a signal of fresh water and renewed plant growth. The smell of rain, calling something ancient in us. Petrichor, rain on dry earth. The scent of water returning. Gently moving forward, toward the largest scales. While this is primarily about the sun, water is intimately connected. The hydrogen atoms in every water molecule were forged in the Big Bang 13.8 billion years ago, in the first few minutes of the universe. The sun, like all stars, burns hydrogen in its core, fusing hydrogen atoms together to form helium, releasing the light and heat that warms our planet and drives the water cycle. In this way, the hydrogen in the water on Earth is the same kind of hydrogen that fuels the sun. The energy that evaporates ocean water into clouds comes from the very process that is slowly consuming the hydrogen, the same element that is part of every water molecule. Water and sunlight are made of cousins. The energy that moves water around the planet comes from the burning of its own ingredient. Astronomers have detected water ice in the disks of material that surround young stars, the same kind of disks from which planets eventually form. In some systems, there is a boundary called the snow line, beyond which temperatures are cold enough for water to freeze. Inside the snow line, close to the star, it is too warm for ice to exist. Beyond it, water freezes onto dust particles, and these icy particles can stick together and eventually form icy planetesimals, the building blocks of planets and moons. In our solar system, the snow line was approximately in the asteroid belt between Mars and Jupiter. This is why the outer planets and their moons tend to be icier than the inner rocky planets. Water ice quietly building the architecture of planetary systems from the very beginning. While the oceans hold about 1.3 billion cubic kilometers of water, some estimates suggest that there may be several times that amount of water stored within the Earth's mantle, the layer of rock between the crust and the core. This water is not in liquid form, but is bonded into the crystal structure of certain minerals, particularly a mineral called ringwoodite. A sample of ringwoodite brought to the surface by a deep volcanic eruption was found to contain about 1.5% water by weight. If that is representative of the mantle as a whole, the total amount of water in the mantle could be several times the volume of all the surface oceans. This deep water cycles slowly between the mantle and the surface over millions of years through volcanic outgassing and the subduction of hydrated oceanic crust. The Earth itself, holding water deep in its body. Comets are small bodies in the outer solar system composed primarily of ice, frozen water, carbon dioxide, methane, and ammonia, mixed with dust and rock. When a comet travels close to the sun, The ice on its surface warms and sublimes directly from solid to gas, creating the characteristic bright tail, or coma, that we can sometimes see from Earth. The term dirty snowball was coined by astronomer Fred Whipple in 1950 and remains an apt description. Comets are thought to be some of the most primitive objects in the solar system, leftover material from its formation 4.5 billion years ago, and studying them gives us a window into the conditions of the early solar system. The Rosetta spacecraft spent years traveling to and orbiting a comet, and the Philae lander touched down on one. A spacecraft landing on a snowball 4.5 billion years old, drifting in the dark beyond Mars. Over millions of years, a gentle snow of material has been falling onto the ocean floor. Tiny shells of marine organisms, particles of wind-blown dust, microscopic mineral grains, volcanic ash, all slowly drifting downward through the water column and settling on the bottom of the sea. This sediment accumulates at a rate of a few centimeters per 1,000 years in most places. In some areas, the layer of sediment is several kilometers deep, recording hundreds of millions of years of Earth history. Scientists drill down through these sediment layers and pull up cores, reading the ancient history of Earth's climate, chemistry, and biology layer by layer, millimeter by millimeter. The ocean floor is a library, written in sediment, quietly recording everything that has happened above it, for as long as there has been an ocean. Let us take a very quiet moment to rest here, in the deep, still, silent ocean floor. Of all the water on Earth, about 97.5% is salt water in the oceans. Only 2.5% is fresh water. Of that 2.5%, about 69% is locked in glaciers and ice caps. About 30% is groundwater. Only about 0.3% of Earth's fresh water is in rivers, lakes, and swamps on the surface, the water that is most directly accessible to land-based life. So the rivers, lakes, ponds, and streams that we know and depend on represent an extraordinarily small fraction, less than 0.01% of all the water on Earth. The water you drink, the water that falls on your garden, the water in the rivers where fish swim, all of it is contained in that tiny sliver. This small, precious fraction, something to hold gently, to take care of, to be grateful for. The leaves of the lotus flower and many water lilies have a surface that is remarkably water repellent. Water does not spread across the leaf. It beads up into near-perfect spheres and rolls off. This property, called superhydrophobicity, is due to the microscopic structure of the leaf surface. It is covered in tiny waxy bumps, and water droplets sit on the tips of those bumps, touching only a tiny fraction of the leaf's actual surface. Dirt particles and debris are picked up by the rolling water droplets and carried away. This self-cleaning property, called the lotus effect, has inspired engineers to create self-cleaning surfaces, anti-icing coatings, and water-repellent fabrics. Nature had already discovered the optimal microarchitecture for repelling water, millions of years before materials science existed as a discipline. The lotus, clean in the muddy pond, quietly perfect. Pure water freezes at 0 degrees Celsius. But salt water freezes at a lower temperature. The more salt it contains, the lower its freezing point. Seawater, with its approximately 3.5% salinity, freezes at about -1.8 degrees Celsius. This is why roads are treated with salt in winter. The salt lowers the freezing point of the water, helping to prevent ice from forming. And in the ocean, it means that even when surface temperatures drop slightly below zero in cold winters, the ocean does not freeze solid. It requires temperatures well below zero for sea ice to form. When seawater does freeze, the salt is largely expelled from the ice crystals, so sea ice is relatively fresh. The salt stays behind in the remaining water, making it salter, denser, and causing it to sink, driving the global ocean circulation currents we discussed earlier. Salt and water, working together in the global system. We often think of tropical rainforests as the most important carbon-storing ecosystems on Earth, and they are extraordinarily important. But wetlands, particularly peatlands, which are waterlogged areas where plant material accumulates over millennia without fully decomposing, store carbon at an even higher density. Peatlands cover only about 3% of Earth's land surface, but they store about twice as much carbon as all the world's forests combined. The waterlogged conditions prevent the normal decomposition of dead plant material, and over thousands of years, a deep, dark layer of compressed organic material called peat builds up. This peat is essentially a record of thousands of years of plant growth, slowly compressed by the weight of more plant growth on top. Water, by preventing decomposition, has been quietly building one of the largest carbon stores on Earth. At the bottom of the ocean, in some of the darkest, deepest, most remote places on Earth, hot water seeps from cracks in the ocean floor. These are hydrothermal vents, and they are one of the most extraordinary environments on the planet. The water emerging from them has been heated by the Earth's internal heat to temperatures of several hundred degrees Celsius, and it carries dissolved minerals from deep within the rock. Around these vents, in complete darkness, far from any sunlight, communities of life exist: bacteria, tube worms, clams, shrimp, fish, fed not by sunlight, but by the chemical energy in the minerals carried by the vent water. Some scientists believe that hydrothermal vents may be where life on Earth began, billions of years ago: hot, mineral-rich water, providing the energy and the chemical building blocks from which the first self-replicating molecules assembled themselves. Water, deep in the dark, perhaps present at the very first moment of life. Now, as we continue, moving quietly, almost to the end of our journey, when water is perfectly still, its surface acts as a perfect mirror. The reflection in a calm lake can be so precise that you can sometimes struggle to determine where the real sky ends and its reflection begins. This perfect reflection is a consequence of the smooth, flat water surface. Light bounces off it at the same angle it arrives, creating an exact, inverted image of whatever is above it. Ancient peoples used bowls of still water as mirrors, long before polished metal or glass mirrors existed. The reflection in still water was one of the first mirrors human beings ever used. And there is something deeply restful about a still lake reflecting the clouds, the trees, the sky, doubling the world, making it larger and quieter, turning the sky both above and below, surrounding you gently in reflected light. The Pacific Ocean is the largest ocean on Earth, and it is so vast that it covers more area than all of Earth's continents and islands combined. Its area is about 165 million square kilometers. If you were to fly in a straight line across the widest point of the Pacific, from Southeast Asia to the coast of South America, you would be flying for more than 20,000 kilometers, almost entirely over water. It contains more than half of all the water in all the world's oceans. It is, in some ways, the defining feature of the planet, a vast, deep, ancient body of water that dwarfs the land. From space, when the Pacific faces the viewer, Earth looks almost entirely blue. An ocean planet, a water world, the land merely islands in the enormous, quiet sea. The sound and sight of flowing water has been used as a focus for meditation and quiet contemplation in many cultures across thousands of years. Japanese garden design often incorporates the sound of water: a bamboo fountain, a small stream, a carefully placed waterfall, as a means of creating an atmosphere of calm. In many Indian and Southeast Asian spiritual traditions, rivers are considered sacred, and their sound is used as an object of meditation. The sound of water, gentle, continuous, soft, occupies the mind enough to quiet it, filling the attention without demanding it. It is neither too stimulating nor too dull. It holds you gently. And right now, wherever you are, if you can imagine the sound of a small stream, or gentle rain on leaves, or soft waves on a shore, You can perhaps use that sound to let your thoughts slow down even further. Slowly, gently. In the early solar system, water played a significant role in how planets formed. In the region beyond the snow line, where temperatures were cold enough for water to freeze, water ice-coated dust grains and helped them stick together, forming larger and larger aggregates. These icy grains and aggregates eventually accumulated into comets, asteroids, and eventually the building blocks of the outer planets and their moons. The giant planets like Jupiter and Saturn are believed to have formed cores of icy material before accumulating their massive gas envelopes. In this way, water, or rather, ice, was one of the key construction materials of the solar system. It helped things stick together in the cold and dark, far from the sun, building worlds. Water is glue. Water is foundation. Water, present at the very beginning of world-making. Limestone caves are created by slightly acidic water dissolving away rock, slowly, over vast stretches of time. When carbon dioxide in the atmosphere and soil dissolves into rainwater, it forms a weak carbonic acid. This mildly acidic water, seeping into limestone, slowly dissolves the rock along cracks and joints. Over thousands and hundreds of thousands of years, tiny cracks become passages, passages become chambers, chambers become the great, echoing cave systems that spelunkers explore today. Lechuguilla Cave in New Mexico has been forming for at least 4 million years. The Mammoth Cave system in Kentucky is thought to be at least 10 million years old. These vast, dark, silent spaces were made by nothing more than slightly acidic water, flowing through cracks in rock, dissolving a little bit of stone with every passing year. Patience beyond all human comprehension. And we can take a moment to notice the great, long patience of water, dissolving stone over millions of years, the same water, always moving. Every molecule of water in your body right now has an extraordinarily long history. Before it was in you, it may have been in the ocean. Before the ocean, in a cloud. Before the cloud, in a river. Before the river, in the soil. Before the soil, in a plant. Before the plant, in a rain puddle. Before the puddle, in a glacier. And before any of that, it may have passed through the body of countless other living organisms, bacteria, fungi, fish, dinosaurs, ancient ferns. Each water molecule moves through the water cycle endlessly, passing in and out of living bodies, resting in oceans and ice, rising as vapor, falling as rain, soaking into soil, being drunk, being exhaled, being absorbed by roots, being released through leaves. The water in you is not just yours. It has always been shared. You are part of the water cycle, as much as any river or cloud. While much of Earth's water is thought to have arrived via comets and asteroids, some scientists have proposed that a portion of Earth's water may have formed right here, on Earth itself, through chemical reactions in the young planet's interior. In the early Earth, as hydrogen from the solar nebula, the cloud of gas and dust from which the solar system formed, was incorporated into the rocky material of the planet, it could have reacted with oxygen-bearing minerals to form water. This water, formed in the deep rock, could have gradually outgassed through volcanic activity, contributing to the early oceans. If this is correct, then some of the water on Earth was not delivered from elsewhere. It was made here, from the raw ingredients of the young planet, born from the Earth itself, homegrown, as old as the rock beneath your feet. The ice ages that have periodically gripped the Earth over the past few million years are partly driven by subtle, regular changes in the shape of Earth's orbit around the Sun and the tilt of Earth's axis. Cycles known as Milankovitch cycles, named after Serbian astronomer Milutin Milankovic, who described them in the early 20th century. Over periods of tens of thousands to hundreds of thousands of years, the eccentricity of Earth's orbit, the tilt of its axis, and the direction in which its axis points all change slowly. These changes affect how much sunlight reaches different parts of the Earth in different seasons. When the changes align in certain ways, Summers become cooler and less snow melts. Snow and ice accumulate year over year, and eventually ice sheets spread across the continents. The water cycle, responding to the slow dance of Earth's movement around the sun. Carbon dioxide gets most of the attention when it comes to greenhouse gases, but water vapor is actually the most abundant and most powerful greenhouse gas in Earth's atmosphere. Water vapor absorbs outgoing infrared radiation from Earth's surface and re-radiates it back downward, warming the planet. It accounts for roughly half of the total greenhouse effect that keeps Earth warm enough for life. The amount of water vapor in the atmosphere is closely linked to temperature. Warmer air holds more water vapor. This creates a feedback loop. As temperatures rise for any reason, more water evaporates, more water vapor accumulates in the atmosphere, and this additional water vapor warms the planet further. This is called the water vapor feedback, and it amplifies other climate changes. Water, not just the medium of life, but also a powerful regulator of the temperature of the entire planet. And so we come to the final thought of our long, quiet journey. Every drop of water on this planet, every molecule in the ocean, every snowflake on a mountaintop, every droplet in a cloud, every molecule moving through your blood right now, is part of one connected, continuous, endless system. The water cycle is not something that happens out there in the world, separate from us. We are inside it. We are made of it. When you breathe out, you add water vapor to the atmosphere. When you drink a glass of water, you incorporate ancient ocean water into your body. When rain falls on a garden, it may once have been part of a glacier or a tropical rainstorm, or the tears of some creature that lived millions of years ago. Everything is connected through water. Every drop of rain is a returned pilgrim. Every glacier is a library. Every ocean is a memory. And you, resting now, are made mostly of water, part of this one great, slow, endless journey that has been flowing since before the Earth was born. Gentle wind down. Now, as we slowly, gently come to the end of our journey tonight, we have traveled a very long way together. From the ancient origins of water in the cold of space, to the depths of the ocean, to the clouds above us, to the rivers that have shaped the mountains, to the water moving quietly through your own body right now. We have thought about small things, a single water molecule, the shape of a raindrop, a tiny beetle on a sand dune, drinking the morning fog. And we have thought about vast things, oceans larger than all the land on Earth, water in ancient meteorites, a moon of Saturn spraying water into space, ancient water sealed in rock for 1 billion years. And through all of it, through every quiet fact and every gentle thought, water has been the same. Patient, moving, connecting everything, carrying life, returning, always returning to where it began. There is something very calming about that continuity. Water is not in a hurry. It has been on this journey for 4 billion years, and it will continue long after any of us. It does not rush. It flows around obstacles. It finds the lowest path. It takes the long way, and the long way always leads somewhere. And right now, the water in your body is resting, settling into stillness, just as water settles when the wind dies and the surface goes smooth. Your blood is moving quietly through its slow circuits. Your brain is resting in its gentle fluid. The cells of your body are each wrapped in their own tiny ocean, quietly doing the work that keeps you alive. You are made of water. You are, in so many ways, the water cycle itself, taking it in, moving it through you, releasing it back into the world. And tonight, as you drift off to sleep, the water in you is at peace. The rain is falling somewhere in the world tonight. The ocean is breathing with the tide. A glacier is moving very slowly under cold starlight. A cloud is forming over the sea. A river is flowing toward the ocean over smooth stones in the dark. All of it part of the same long, slow, endless journey. All of it connected. All of it quietly, beautifully going on. Slowly, gently, there is nothing you need to do right now. Nothing to think about. Just rest. Just breathe. Just feel the quiet weight of your body, and let the water carry you into sleep. Very slowly, gently, like a leaf on a still river, drifting. Good night. Thank you very gently for spending this time here. If this video brought you some peace, a quiet like and subscribe would mean a great deal. But there is no rush. Rest now. We will be here when you return. Good night.